Okay, so we're going to have a look at another question. This one comes from the topic of ordinary differential equations. So we've seen quite a few differential equations so far. This question says solve the following. We are asked to solve y double prime plus y is equal to e to the x plus x cubed, and we're told in terms of initial conditions, so we have some initial conditions here, y of 0 is equal to 3 and y prime of 0 is equal to 0. Now this is quite a technically difficult differential equation. This is a very spicy differential equation. There's a lot that we need to do here. We first need to find a general solution to the dE. We then need to find particular solutions to the dE because of the e to the x plus x cubed. We then need to find values for all of the coefficients in both the particular solution and the general solution. Once we've done all of that, we then need to confirm that it is in fact the solution. There is going to be a lot of working in this video. If you lose or gain a sign anywhere, everything will go wrong. Right? So we've got to be very careful not to lose or gain any signs or numbers or terms. We have to add things correctly, multiply things correctly, write the numbers clearly, write your signs properly, keep track of them. Right? Otherwise this will go horribly wrong. So first, we have the dE, y double prime plus y equals 0. So this is an equivalent dE. And we're going to solve this using characteristic polynomials. So this is r squared plus 1 equals 0. Well, this implies r is the positive negative square root of minus 1. This is positive negative I. Now, if this is of the form alpha plus beta I, we find that alpha is equal to 0 and beta is equal to 1. Now, when the characteristic polynomial has imaginary roots, the general solution, so if r1, 2 are imaginary, we find that the general solution to such an equation is y is equal to a times e to the alpha x times cosine of beta x plus b times e to the alpha x times sine of beta x. Now alpha here is 0, beta is 1, so we plug this in, we get y general, our y general solution is a, e to the alpha x is 1 because alpha is 0, so a cosine beta x is just x because beta is 1, plus b, e to the alpha x again is 1, times sine of x. This is our general solution. So this is the general solution that we've got so far for our ordinary differential equation. We now need to find the particular solution and or particular solutions. So we have two functions over here on this side. We have e to the x and x cubed. We have to guess in order to find particular solutions. If we have a function of the form, so if function is equal to x to the n, then the logical guess is a n x to the n plus a n minus 1 x to the n minus 1 all the way down to a naught. If the function is of the form e to the alpha x, then the logical guess is a e to the alpha x. So because we have the sum of these, we are going to take the sum of both of these guesses and assume that this is our particular solution. So for our particular solution, we get y particular is equal to a e to the x. In this case, the alpha is 1 because this is just an x up here, plus b x cubed plus c x squared plus dx plus e. And this is our particular solution. Now we're running into a bit of a problem in this question already. We've used a and b up here, so we're not going to use a and b here. We're going to change these coefficients. So y particular is going to be c e to the x plus d x cubed plus e x squared plus f x plus g. And this is our assumed particular solution. Now, when we get a particular solution, we can find values for these coefficients straight away by taking the first and second derivative of the particular function, plugging them into the function we have over here, and then mapping the coefficients to one another. So using what's called coefficient comparison. So let's take the first derivative. We get y prime of particular is c e to the x plus 3 dx squared plus 2ex plus f. And the second derivative, y double prime of particular, is c e to the x plus 6 dx plus 2e. We're going to plug them in to the dE. So we know that y double prime plus y is equal to e to the x plus x cubed. Notice the number in front of the e to the x is a 1, the number in front of the x cubed is a 1. So y double prime particular is this, c e to the x plus 6 dx plus 2e plus y, which is this, c e to the x plus dx cubed plus ex squared plus fx plus g is all equal to 1 e to the x plus 1x cubed. Now we need to group terms on the left-hand side. So we get e to the x times 2c plus x cubed times d plus x squared times e plus x times, well, we've got an f here and a 6d here. So 6d plus f plus 2e plus g. 2e plus g. This is all equal to e to the x times 1 plus x cubed times 1. Now, in the case where we're doing a comparison of coefficients, we're assuming that any coefficients that don't appear on the right-hand side are equal to 0. So we get, and essentially we're saying, so just to demonstrate this graphically, let me pick a slightly better color for this, maybe this blue color. 2c is going to be equal to 1. d is going to be equal to 1. All of the other coefficients, e, 6d plus f, and 2e plus g, these are all going to be equal to 0 because they don't appear on the right-hand side. So we get the following equations or identities coming from this expression. We get that 2c is equal to 1. This implies c is equal to 1/2. So we found the value for c. We get d is equal to 1. So this has found the value for d. We get e is equal to 0. This has found the value for e. We get 6d plus f is equal to 0. This means f is minus 6d. Given that d is 1, this means f is minus 6. And we also get 2e plus g is equal to 0. Now we know that e is equal to 0. This implies that g is equal to 0. So we've found c, d, e, f, and g. We have these values. Now we can plug all of these into our particular solution. So this means that y particular is now equal to, well, this was our y particular up here, c e to the x, and then the polynomial. So we get c e to the x 1/2 e to the x plus dx cubed, that's 1x cubed, plus ex squared, so there's no x squared, plus fx, so minus 6x, plus g. So this is our y particular in this case, with identified coefficients, 1/2 e to the x plus x cubed minus 6x. And so now we can find a full solution. Now we add y general and y particular, and this will equal y full. So this will be our full solution set. So this implies y full is equal to the general, which we found all the way up here, found ages ago, was a cos x plus b sin x. We've long since forgotten about this. So a cos x plus b sin x, and then we have to add to this our particular solution, which is plus 1/2 e to the x plus x cubed minus 6x. This is our full solution. So the majority of our work, or quite a lot of the work in this question, is now done. We've now found a full solution to this DE, but we've been given initial conditions. And so we can take the first and second derivatives of this full function, or in this case we only need the function and then the first derivative. We can take the function and then the first derivative, evaluate them at these initial conditions. This will let us solve a and b. When we have a and b, then we will have our completely evaluated full solution, and then we can take its first and second derivatives, plug them back into the initial function to check that it is in fact correct. So we've got to find the first derivative here, and then evaluate the function and the first derivative at the initial conditions. So let's evaluate the function at this initial condition first, then do the derivative and evaluate the second one. So we have y of 0 equals 3. This implies that 3 is equal to a times cosine of 0 plus b times sine of 0 plus 1/2 e to the 0 plus 0 cubed minus 6 times 0. This is 0, this is 0, sine of 0 is 0, so this term goes away. E to the 0 is 1, cosine of 0 is 1, so we get 3 is equal to a plus 1/2. So this seems to be correct. We've got to be very careful when we're doing this. We have to make sure that we have all the right values here. So we minus 1/2 from both sides. Minus 1/2. 3 minus 1/2 is going to be 2.5. That's 5 on 2. So this tells us that a is 5 on 2. And now we're going to have to take the first derivative. So y prime of the full solution. A cosine x, cosine becomes minus sine, so this becomes minus a sine x plus b sine x, that becomes b cosine x. 1/2 e to the x stays as 1/2 e to the x. X cubed becomes plus 3x squared. 6x becomes minus 6. We now have to evaluate this at the point where x is 0. So this implies that 0 is equal to minus a times sine of 0 plus b times cosine of 0 plus 1/2 times e to the 0 plus 3 times 0 squared minus 6. Now we're going to be very careful here. We have a few different negatives floating around. This gives us 0 is, the a term goes away because sine of 0 is 0. Cosine of 0 is 1. So we have b. E to the 0 is 1. So that's plus 1/2. This term goes to 0 minus 6. So we're going to add 6 to both sides. This gives us b plus a half is equal to 6. Going to minus a half from both sides. This gives us b is 5.5. That's 11 on 2. So b is 11 on 2. So we have now found a value for a, and we have found a value for b. So now we can plug them in. So this means our fully evaluated solution, y full, is going to be equal to a cosine x. A is 5 on 2. So it's going to be 5 on 2 cosine x plus 11 on 2 sine x plus 1/2 e to the x plus x cubed minus 6x. So this is the y full solution we had up here, but we've now found the a and b values. So pretty much at this point the question is mostly done. This is the answer that we're after. But as we have done consistently through these examples, we like to check. Right? You can check once you're at the university level. You should be. It's a whole lot of work, but you should be doing it. Right? It's hard because it's a lot of work. You have to do a lot of work consistently, but it's a good habit to be in, especially if you're in an exam. If you're in a first or second year engineering calculus exam, DE's exam, you want the questions right because you need to do well in that course, right? You need to get every mark you can to even pass. A lot of those courses are incredibly rigorous. So if you can check your answers in the exam, you should be, because that means you're getting them right. If you notice the check fails, then you've done something wrong. Then later in the exam, you can come back to that question, try it again. So we'll take a first derivative. So y prime of the full solution, cosine becomes minus sine, minus 5 on 2 sine of x, plus sine becomes cosine, 11 on 2 cosine of x, plus 1/2 e to the x, plus 3x squared minus 6. The second derivative, y double prime of f, or y double prime with f subscript, implying that this is our full solution. Minus sine becomes minus cosine, minus 5 on 2 cosine of x. Cosine becomes minus sine, minus 11 on 2 sine of x. Then we have plus 1/2 e to the x plus 6x, and the minus 6 goes away. So this is our function up here. We have our first derivative here, and then we have our second derivative down here. Now we need the second derivative in the function. So we have y double prime plus y. This is apparently equal to e to the x plus x cubed. So we get y double prime is this, minus 5 on 2 cosine of x minus 11 on 2 sine of x plus 1/2 e to the x plus 6x. We have to add to this y. So plus y, which is this function up here, plus 5 on 2 cosine of x, plus 11 on 2 sine of x, plus 1/2 e to the x plus x cubed minus 6x is apparently all equal to e to the x plus x cubed. Well, we have minus 5 on 2 cos x plus 5 on 2 cos x, minus 11 on 2 sine x plus 11 on 2 sine x, minus 6x plus 6x. On the left-hand side, we're left with 1/2 e to the x plus 1/2 e to the x plus x cubed. This is apparently equal to e to the x plus x cubed. Well, this is definitely equal. 1/2 e to the x plus 1/2 e to the x is e to the x. E to the x plus x cubed is equal to e to the x plus x cubed. And this is true. This is a fantastic result because this confirms that the full solution we calculated over here on the right-hand side of the screen, this is in fact the correct solution. So you can do this check yourself. Once you've found your solutions with all your values, you can then differentiate again, plug it all in, simplify it, and solve. You can also check using some kind of computing platform. So you can get a computer program or a computer web page that solves DEs. You can put it in and confirm it. We did this manually. We found this. We checked it manually, so we don't need to do that. But this is definitely the solution to this particular differential equation. And this is quite a difficult differential equation. These types of differential equations can be fairly difficult just because there's so many terms. If you lose or gain a number, lose or gain a sign unnecessarily, it's very hard to tell because there's so much going on. The minute you lose or gain a sign and you don't notice it and you move past it and it's built into your working, probably your answer is going to be wrong. And if you're lucky, the check will reveal that you were wrong. If you're unlucky, you'll do the check, it will still pass, but you'll have the wrong answer, right? Because there are parts of the question that you can get that don't show up in the check, right? The check is not completely perfect. It's pretty good because it means that this does work, but it's not absolutely perfect, right? So you do need to be very careful with these questions.